Okay, I'm back. This is going to be a much shorter, less rambling, let's hope, video, in which we're just going to go over 2 example problems with speed and a little bit with velocity to help make that more comfortable. Again, we're going to talk about some of this in class. This is experimental. I don't know how it's going to be with a mask, especially if you're in the back of the room. So here it is on video where you can see me a little bit more clearly, hopefully hear very well. And then if class works out better, we'll switch it over to doing it in class all the time. Okay, so sorry, I have my notes so I get the numbers right. I'm starting with example problem 1, and then I'm going to refer back and explain the equations a little bit better. So example problem 1 says the position of a runner as a function of time is plotted as moving along the x-axis of a coordinate system. So that's a really long way of saying somebody's running horizontally, like level ground, nice level run. Like if you're running anywhere within a couple blocks of school, you'd be doing that. Well, a couple blocks north. And so the runner is running for a 3-second time interval. So we would say she's running for 3 seconds. This is a very short time interval, at least in my world of running. That's really quick. And the runner's position changes from x equals 50 to x equals 30.5 meters. What is the runner's average speed and velocity? Okay, so the runner starts, I'm going to put the proper notation on this, but let's just put words for it first. The runner starts at 50 meters, like on a number line. She's standing, let's say this was real nerdy, and I have this huge measuring tape that I'm stretching out. She's standing out there on 50 meters, and she's running actually kind of back towards 0. So she ends the 3-second interval at, what was it, 30.5 meters. Okay? And so they ask us to find the average speed and the average velocity of the runner as she goes from 50 meters to 30.5 meters. And I just realized I don't have a calculator down here. Blast. We'll come up with it. Okay, so her speed. Speed is simply distance divided by time. So when we go to find her distance, if she goes from 50 meters to 30.5 meters, she's run just slightly less than 20 meters, right? So this is 19 point, this, remember, you're watching me do this with no calculator, so this could be embarrassing. But let's say 19.5 meters is her distance. And she does it, they tell us, in 3 seconds. And so her speed would be, I don't know what that is, 6 and then 1.5 divided by 3. Is it 6.3? Okay, if I'm wrong, that is so super embarrassing. But 6-ish meters per second is her speed. So we simply take her entire distance and we divide it by the time it takes her to go that far, right? Now, velocity. Velocity, I mentioned in the last video, is displacement divided by time. Displacement we mathematically write as x minus x naught. This is what I had up on the board and did not explain well. X is our final position. X naught is our initial position. You might have seen like xf minus xi. I don't know if you've seen that ever. And I'm just writing that same thing. This is the preferred notation. This is what colleges use if you would take like AP or if you go into study engineering or something like that. This is just slightly more formal notation. So when I'm talking about x, this is your final position. X naught is this little sub-zero, is your initial position. So over here we say she starts at 50 meters. That's her initial position. So x naught is equal to 50 meters. And she ends at 30.5 meters. So that is her final position. Okay? So when I go to find her velocity, I put those numbers in. I take final position, 30.5 meters, minus my initial position, 50 meters, and I divide it by the time. Now, as you can see, it's really going to end up being the same thing as speed, except her displacement is negative. So it's negative 19.5 divided by 3, which is approximately negative 6.3-ish, if I can do simple calculations in my head. And that negative sign is important. That negative sign is saying, like, she's running backwards. She started at 50 and she's running towards 0. So on a number line, you think of that as backwards. So that is the difference between speed and velocity. Now, the second, my battery's running low, so hopefully we can get this second one in. The second problem is just with speed, and I'm just going to start to set this one up. I might not even finish the whole thing. But there's one in the first problem set we're going to work on in class. You might end up finishing up at home on Thursday. And so it's a little, could be a little tricky, so I wanted to walk through one like it to you, or with you, I'm sorry. So it says you're driving home from college steadily at 65 miles per hour for 130 miles. And then it starts to rain, and so you slow down to 55 miles per hour. And you arrive home after driving 3 hours and 20 minutes for the whole trip. This is before and after rain. And so the question is, how far is your home from school? So we want to know what's your total distance traveled, basically. How far is home from school? And what was your average speed for the trip? Okay, so there's nothing about velocity in this problem. We are using one equation and one equation only, and that is that speed is distance divided by time, which is a very simple equation. However, this problem is a little bit more involved because you're going one speed, then you're going another speed, and so they want us, again, find the total distance and our average speed. So I just want to caution you here, because if I gave, well, I've given the problem with no instruction and just, like, you know, assume people could figure it out. And some of you right now could probably dive in and get it, but I think that a lot of you would say, oh, she was going 65 miles an hour, and then it rained, she's going 55 miles an hour, average speed 60, boom. And that's not right. You cannot assume that. And so if you were sitting here in front of me, I would say, why? And I would give that awkward pause while you think. And you, somebody, hopefully you watching this, would say, well, you can't just say it's the average of the two, because we don't know that she's doing half the trip at 65 and half the trip at 55, right? So imagine if you're driving to school and you're driving 65 miles an hour until you hit the, this would be so unsafe, don't do this, but until you hit the block before school, and then, oh, you slow to 25. You can't say that your average speed for that whole trip is the average of 25 and 65, because you were doing the 65 for a much larger chunk of the trip. So that's the issue here as well. So what I would do is split my quantities up into, before, I'm going to make a little table of it. Before rain, after rain, or when it's raining, whatever. And then, like, let's look at the whole trip. And there's essentially 3 quantities we know about. We know about speed, distance, time, okay? So, like, before it rains, we know, whoops, I can't write the right number, that we were going 65 miles per hour. After it rains, we know we were going 55 miles per hour. Before it rains, we went 130 miles. We don't know how far we went once it stopped raining. And then we know our entire time for the trip was 3 hours and 20 minutes. We want to convert that, so it's going to be like, that's 3 1/3 hours, so like 3.33. Something I didn't say to you in the last video, I'll say this again Thursday. In physics, this is going to be tragic. I know you're all going to start crying at home. We don't use sig figs. Sorry if you're so bummed. And that's not even me being cool, that's just physics. So, I don't know, like 2 decimal places is good for me. Okay, so for the whole trip, what we want to do is find what was your average speed for the whole trip and what was our total distance for the whole trip. And so, if I were looking at this, now that I have the material chunked, I was chunking the material, which makes it much more approachable. You always start where you have the most information, which in this case is before rain. I know my speed, I know my distance, I can easily find my time, right? So if I use the speed equation, I can say, oh, I went 65 miles per hour, 130 miles. If I'm going to solve for time, you'd rearrange this. Again, I'm kind of only just showing a little bit because this is a really simple equation. When we do legit algebra, I will be a much better teacher. But if I rearrange this, I say time is equal to distance divided by speed. So 130 divided by 65 is a nice even 2. So I was going 2 hours before it rained. if I went 2 hours before it rains and I know I go a total of 3.33 hours, well, suddenly I can find how far I went when it was raining. I went 1.33 hours. And so you can see where I'm going with this. I'm going to stop it here because we're going to solve one in class as well. This is a little bit different. But now I have enough information to find my distance once it's raining, right? Just using the speed equation. So distance is speed times time. That would give me the distance once it's raining, which gives me my total distance, and then I can find my total speed. My total speed would be my total distance divided by my total time. So just when it comes to speed stuff, I wanted to show you a problem, sort of a part of a problem like this, because again, it's such a simple equation. You've all worked, I know you've worked with it before you start watching these videos. You can rearrange that and it's easy peasy, I hope. But you can see the questions can get a little bit more complicated. So be careful with that, and especially be careful with assumptions. You can't say, okay, if I was going this speed and then this speed, my average is the average of these two numbers. You have to look at how much of the trip, both in terms of distance and time, occurred at each of these speeds in order to find your true average speed for the whole trip. And I will stop there.